first, the introduction. So that this is a collaboration work done by Heli Laaksonen. She is the director in photogrammetry in the National Land Survey of Finland, and then there is on the production side, and then there is Dr. Lingli Zhu, also actually participating the event, so that if you have some special questions to Lingli most likely can also provide answers, and then by me. And Lingli Zhu and me are working on this research side of the National Land Survey of Finland. So what I will talk about is to give you just a short introduction to this ATMO 2021 project. So that's the project where we try to implement these artificial intelligence methods to this topographic data collection, and then I give you some details about the project resources and schedule and so on. And as the background setting, so that this is a thing that most likely is more or less the same with all national mapping authorities around the world. So that how this far the topographic data collection has been done, at least here in Finland, is mostly based on manual interpretation, manual reading of aerial images, and of course as stereo models. But then so that part of that work is done purely based on these just these raw stereo models, and in that sense without any directing where to focus. But then there is also other ways of gaining information, and those are the different types of hints of the updated features provided by municipalities. They can be provided by other topographic data producers and even by citizens. But all of this digitization or collecting features to the database is basically a manual work, so that there always has to be a human who checks the changes, and while observing them to be real, then mapping them manually to the database. And then in principle, there is the rule that what cannot be seen in the images will be checked later on site. But of course, this is part of the work that basically has less and less resources every year. So that because this is maybe the most time consuming part of the mapping work. Of course, also in that sense, very important part that sort of the superior quality can be only reached by these real on-site manual checkings. But then on the other hand, most likely all Western countries are struggling with the public funding, so sort of decreasing public funding resources, and there is basically, at least in Finland, less and less money for doing this type of work, where basically the demands are getting higher and higher. People want to get more accurate data and more up-to-date data. But then the paradox at the same time is that there is less and less monetary resources for doing it. So, but what has happened in Finland is that there is now the new National Aerial Image Program that started in 2020, and there the goal is that the whole of Finland is covered every 3-year interval with the aerial photographs, with images having 30 or 40 centimeter resolution, and after auto rectification they have 50 centimeter resolution. And here the goal is that more than 110,000 square kilometers get photographed every single year. And then considering the size of Finland, this would give us roughly the cycle of 3 years to get the whole country mapped again and again by these aerial photographs. Then there is also this new national Lidar program, which also started in 2020. And there the goal is that more than 55,000 square kilometers of Lidar data gets collected every single year. So that this is, you can see directly that it's half of the goal set for the aerial photographing, and this gives for the whole of Finland then 6-year cycle that the whole country can be scanned again. And of course, what is a huge improvement for Finnish data collection is that now the new data collection specifications gives us data that has 5 Lidar echoes, Lidar points on every single square meter, compared to our earlier Lidar program that provided 0.5 points per square meter. And this is maybe the data that many of you might be familiar with, because it is shared as open data for everybody. So this 0.5 meter data, so that all Finnish citizens, but basically also for every other people who is just able to find the data from the National Land Survey's web pages. The data at the moment goes to this automatic ground point classification, of course, that being the most important purpose. There are many other classes. Of course, there are also vegetation points are classified and building points as well. And then hopefully in the near future, we already have the method for creating contours automatically from the data. And this is actually the first of the exercises where this kind of massive automatization is implemented in the data production of the National Land Survey of Finland. But luckily, this contouring is such a task that basically, at least this far, that has not been implemented as a machine learning, so that there are other ways of doing it. But now we are focusing on other features that definitely needs machine learning to be extracted. So that this ATMO project is something that officially started in 1st of January, but in reality we were able to start in a concrete way a couple of months later. So this is a 2-year project financed by the Finnish Ministry of Finance. We are less than €500,000 budget, and the generic goal is to use artificial intelligence in updating of national topographic database. And the special focus feature groups are buildings, roads, and hydrographic features. The aims of the project are to reduce the amount of manual and routine work in the topographic data production, so that this is what I said about this cost savings. Then, of course, the goal is also to improve the accuracy and up-to-dateness of topographic data. Of course, this is also a certain type of innovation action inside the National Land Survey of Finland, and it is an excellent example of how we can collaborate the production side with the researchers. And I would argument that at the moment this is the biggest this type of action that we have in the National Land Survey of Finland. And of course, the fourth goal is to then at the end of the project to provide different types of nationwide training data sets, so that other people can test these machine learning methods by themselves as well. So that in this way, this supports our open data policy, but also the open science policies that we have here in the research side of the National Land Survey of Finland. Here is just the kind of the simple diagram what we plan to do, so that this general pattern is basically always the same. So that first we have to have these labeled data sets. So this is the so-called training data. Now we will use orthophotos, true orthophotos, Lidar point clouds, photogrammetric digital surface models, and different type of vector data sets. Then our goal is to use deep convolutional neural networks for this feature extraction, and by using different types of learning technologies and gaining experience from those. And then at the end, we hopefully have these automatically mapped features. What we have already found out is that even though, so that in principle, the implementation of this in automatic feature extraction is kind of even a routine task, so that there are lots of libraries, lots of ready-made tools to be used in this, but already now we found out how extremely important is this labeled data set, so that it must have the real relevance. And once we start to talk about topographic data, we very quickly realize that sometimes it's extremely difficult to talk in a unique way about the features that we intend to represent in our database. So that what could happen very easily is that if we start blindly doing this machine learning exercise, we very easily come from the garbage in, garbage out setting to something that there is plenty of data that can be just squeezed together, but then at the end, the results might be quite nonsense. The other interesting thing, of course, is that after we have done this feature extraction, then comes this huge question: how do we make these real database items of these features that has been extracted? And this is also a challenge that even at the moment, we don't know exactly how much do we need to do effort on then at the end kind of cleaning the data to make it appropriate for our database representation. Here are just a couple of examples of what we did in a very, very early preliminary phase of the project. So that this was the exercise where we just took the orthophotos from the National Land Survey of Finland, also the building polygons, and used those as training data, and then looked what comes out. And even though this quickly looks very promising, so that it looks that most of the buildings are quite well picked from the aerial photograph, but then in reality, what was found out is that of course there was this mismatch in the vector building polygon features and orthophotos that was not true orthophotos. And then what the end happens is that there is a lot of shadows and lots of other things that are included in these building polygons. And of course, for example, here, the first immediate correction would be to use the true orthophoto, where the geometry starts to match with the geometry that we have with the building polygons. And then by using true orthophotos, we get much, much better results when we extract these building footprints. So what are the opportunities? How do we see it? How do we see it at the moment? So definitely there is so that the work that is done now in this ATMU project challenges this traditional way of collecting topographic data, and we hope to gain really good experiences and see the opportunities, but then also see the limitations of this artificial intelligence methods. Then, of course, this big opportunity is this open database for training data, and this provides us the possibility to start to build a network, even international network of the people who are interested about the topic and want to participate the work that way. And there actually the network part was already mentioned as our third opportunity. But now I have spent this 15 minutes so that I thank you all, and then, sorry, I need to scroll back to our agenda just to see that now there is 15 minutes for Emilia Hattula talking about the experiences on selecting data labeling tools for remote sensing data. So please, Emilia, I will turn off my presentation and my camera, and the floor is yours.